So we did our searching algorithms last time. Now the final one in this section is sorting algorithms. And just like with the previous section, we have two to learn and we have to learn the differences. Merge sort, bubble sort, and then compare and contrast. And again, we have to understand the mechanisms of the algorithm. So you should be able to write the algorithm down without any help. You should be able to create a flowchart for it without being told how it works. Now, I've got my same data set from last time, but this time I've unordered it. And we're going to put it into order. So this is going to take a little while, so do pay attention. Bubble sort, what we're going to do is we're going to step through each piece of data, each pair of data points, and we're going to compare them, and if we need to, we're going to swap them around. So first of all, and we're going to keep doing passes of that until the data is correct. So first of all, we go and we compare these two data points. Well, John is greater than Max, so therefore these need to be swapped around. Yes. Okay, I messed up. There we go. They've now been swapped around. Now we compare John and Sophie because we're now in column D. Remember, we're checking after we've already made that change, so it's fine if something bubbles all the way to the top, which is probably what's going to happen here. So now again, John is greater than Sophie, so these need to be swapped. So again, we're going to swap them around. Then we're column E, John and Alice. John again is greater than Alice, so they swap. And then John is compared to Harry because we're in column F. Again, John and Harry swap around. Then John and Emily, they're compared and they swap around. Then John and Alex, again, John is greater than Alex. This is a really easy example because John is greater than everything, so he just sort of percolates up. Well done, John. Now we've done our first pass. Now we go back and we start comparing again. So we say, is Max greater than Sophie? No, these two are in the right place with respect to each other because Sophie is greater than Max, so we leave them be. Now we look at Sophie. Sophie is greater than Alice. Sorry, Alice is greater than Sophie, so these are the right way around, so we'll leave those be. Harry and Alice are no. Harry is less than Alice, so he should be to the left of her because the low numbers should be here and the high numbers should be on the right. So these two get swapped around. Now in column F, Alice and Emily. Same problem. Alice needs to get swapped with Emily, so they get swapped. And then same problem again. And so you're literally just comparing the pairs of values and just seeing pairwise, are these pairs in the right place with respect to each other? And essentially then we get to Alice. Alice is less than John, so Alice is in the right place. Then we go back again and we do another sweep. Max and Sophie are in the right place with respect to each other, but Sophie, when we get to the next stage, is in the wrong place with respect to Harry, so we put Harry there. Remember, the algorithm's blind, so the algorithm can't now see this problem, that these are in the wrong place. It's only looking at the exact pair it's currently dealing with. So now Sophie, is Sophie greater than Emily? Yes, she is, so we swap them. Is Sophie greater than Alex? Yes, she is, so we swap them. And then Sophie's also greater than Steve, so Steve goes here. But Sophie is less than Alice, so Sophie's in the right place. So these are already, all three of these done. You notice every time you do an execution of the bubble sort, the highest value always bubbles up to the top. That's why it's called a bubble sort. John went all the way up to the top, then Alice went all the way up to the second top, and then Sophie. By definition, the highest value will always bubble up to the top. Now we go back again. Harry and Max need to be swapped round. Then Max and Emily need to be swapped round. This is quite laborious to do by hand, but it's worth showing you. Max and Alex need to be swapped around, and obviously you're starting to understand why computers are so useful because they do all this work for us. Max gets swapped around, and then Max is a bit above the top. We go back again. These two need to be swapped around. But then, come on. But then Harry and Alex are in the right place with respect to each other. Then Steve is a problem. Steve needs to go back. Silly Steve. Now this is in the right place, and then we go back again. These two are in the right place, but Steve's not, so we swap these two. And then we go around again. These need to be swapped around. And then now we do a final sweep and make sure that we go through, the program will literally go through each option and if it made no changes, the list is then sorted correctly. Now that took a little bit of a long while, so I'm going to go over it again. The algorithm goes through each element and compares it to the element directly to its right in this instance. That's typically how it works. And if the one to its right is greater than it, so effectively if it's in the wrong place, because every number obviously in an ordered list should be greater than the one to its left. If this number's bigger, that's fine, but if it's less, then you just swap these two data points around. And you do that for every single element in the row, and then when you're done, you go back again and you do it again until it's done. So that is our bubble sort. Oops. Merge sort is a little bit more complicated. So merge sort, there's a picture I found on Wikipedia that shows what's going to happen, and we'll do it in a minute. Essentially, you split the data. It's almost like the opposite of a binary search, really. You take the data, you split it into some sections, then you split those sections, and you keep doing that until you get individual elements, and then you build them up again in the right order with respect to each other. So, how does it actually look? Well, first of all, we separate our data. Let me zoom out one click. So we split it in the middle, which we've done now. Then we take each of these points and we split these in the middle. So let's put that there, that there, these two here, and then these two here. So now we've split the data again. Then we split them up one more time into their individual elements, but they're still sort of pairs, so I actually won't do that, to be honest. But in this graph, they have split them into individual elements. You didn't really need to do that. You could just shuffle, like a bubble sort, just compare it to the one next to it. So just like a bubble sort, just compare John and Max. Are they the right way around? No, they're not. So let's swap them around. Sophie and Alice, they are in the right way around. Harry and Emily, they're not in the right way around, so we're going to swap those around. And then Alex and Steve also need to be swapped around. Great. So now we've ordered these pairs. So each of these pairs is ordered. Now we're going to look at each pair of pairs, essentially. This pair of pairs and this pair of pairs. Let me just draw a box around them so that's a bit easier to understand. So those are your pairs, and then essentially that is a group and that is a group, and we're looking at them as pairs of pairs. So what we would do typically, I think the best way to envisage this is if you zoom in and look at just these ones. We have 4 spaces to fill, and they need to be filled with the 4 people. So what I would do is I would say compare the 2 first values and see which is lowest. Essentially, we're just adding them in order, but the way that computer will probably do this, it would go, well, is Max lowest or Sophie lowest? Because it's going to be one of them. Well, Max is lowest, so let's bring Max down. And then, well, now is John lowest or Sophie lowest? It's Sophie. And now John or Alice, Alice. And then John down there. And now there we have our little group, which is now built and it's in order. And then we do this again here. So same deal. We have 4 boxes to fill. Emily or Steve? It's Steve this time. Emily or Alex? It's Emily. Harry or Alex? Harry. And then Alex. And so now both of these 2 groups are in order. And then now we do the exact same thing on a bigger scale, if Excel is going to behave. We say, right, well, we now have 8. That's 7, isn't it? Yeah, that's 7. We now have 8 boxes to fill, and we do the same thing. So remember, we're always looking at the first one because these are in order, so only the first one is the one we need to worry about. The lowest will always be either Max or Steve. It will never be Sophie because Sophie is always greater than Max. So Max or Steve, got to be Steve. Max or Emily, got to be Emily. Max or Harry, that's Harry. Max or Alex, it's Alex. So notice that all the low ones have already come before any of this, and then we can just, good practice would be still add them independently. And then we've merged them all together and combined them, and so that's your merge sort. And they're in order. So now when you look back at this diagram, it might make a bit more sense. We took the full data set, We split it down into halves. We split each of those halves into halves. We ordered these pairs. We built the pairs up, and then we built those up into our overall set. So that's essentially how a merge sort works. Much like the comparison of linear and binary search, the great thing about merge sort is that if you double the size of the data, you only add one more step of execution because we're halving each time. Also, to anybody who's got quite a good knowledge of hardware, you'll recognize that a multi-core processor or something would be better capable of doing each of these sets on a different core of the processor. I don't think that's on your specification, but that's something we're thinking about. It probably wouldn't put it in an exam because it might not be in the mark scheme, but it's a very parallelizable process would be the term. So bubble sort is the simple one, the one that bubbles them up to the top. It's very good for small data sets. Merge sort is good for big data sets because because of that merging idea, it's halving the data set each time, or doubling the data set makes it half as difficult. Understand how they both work. Compare and contrast, again, as I said with the last one, I don't have an official list, but that's what I would probably say. The main thing is that merge sort is better for big data sets. Much like with searching algorithms, a lot of programming languages will use bubble sort for any set that you try to sort, which is say 20 elements, and merge sort otherwise. So there you go, sorting algorithms.